Hi, everyone. Thank you for the introduction. I'm Jamie New from Carnegie Mellon University, and I'm going to talk about our recent paper, whose title is Accurate Node Feature Estimation with Structured Variational Graph Autoencoder. This paper will be presented at this year's KDD conference, and this work was done with Hyun-Sik Jeon and Jinong Jung and Professor Yu Kang at Seoul National University. This is the outline of this talk. Real-world graphs contain node features such as activity logs of users in a social network or abstracts of papers in a citation network. And many tests on graphs require such node features to acquire high accuracy, such as node classification or rank prediction, and so on. And many graph neural networks also require such node features to make meaningful propagation of information through the graph structure. However, missing features are common in many real-world graphs, such as user nodes in a social network. So in a social network, many users set their profiles private, so it is hard to use such information in doing meaningful graph-based tests. And in this circumstance, feature estimation is essential to utilize node features in large real-world graphs that may contain missing features. This figure illustrates the problem of feature estimation in an example graph consisting of 6 nodes. If we successfully estimate the missing features as in the right graph, then we can gain improvement of accuracy in node classification and link prediction and so on. We define the problem formally as follows. We are given an undirected graph G consisting of the set of nodes and the set of edges, and we assume some nodes in the graph have node features X. And such features can be either discrete or continuous based on the domain of the given graph. And we also assume that we have node labels optionally for some nodes in the graph. This is because discrete labels are often easier to acquire than the feature vectors, and such labels provide additional information to the target nodes that have no features. So such node labels can be given or cannot be given based on the problem settings. So we want to build a model that can work with both scenarios, whether the node labels are given or not. So with this information, we aim to predict the unknown features of nodes in the given graph. Now I'll introduce our proposed approach to solve the problem of feature estimation. I'll start with motivation. So there can be various ways to solve the problem. So we choose a way to formulate the problem as maximizing the following likelihood term. Here, F is our estimator, and X and Y are features and labels, and theta is the set of our estimator F. This equation, this likelihood means that we use the observed features and labels as the target variables of this problem, not as inputs. So given the graph structure A or the adjacency matrix A, we aim to build an estimator that estimates the features and labels of all nodes in the graph, and then we want to compare them with the true observations to update the parameters of the estimator. The question is, how can we maximize the likelihood term? As our main approach, we run variational inference with introducing latent variables G to maximize the likelihood. This variational inference allows us to rewrite the log likelihood term with the evidence lower bound or elbow term, which is represented as this equation. This elbow term consists of 2 other terms, which are colored as blue and green respectively. The first blue term is the conditional likelihood of features and labels, and the second green term is a regularizer on the parameterized distribution of Z based on the prior distribution. So the first term is straightforward because it is just conditional likelihood, or which can be written as reconstruction errors of features and labels, but the important part is the modeling of the second term. So the second term of elbow regularizes the distribution of Z based on the KL divergence between 2 different distributions. This forces our target estimation of Z, or the parameterized distribution of Z, to be closer to the prior distribution, which contains no learnable parameters. This is straightforward because the prior distribution does not include any parameters. So that means that the choice of the prior distribution is very important for determining the amount of regularization on the parameterized distribution of Z. But previous works on variational inference ignore the correlations of latent variables in the graph or just in other problems. So this is done by modeling the parameterized distribution of Z as the Gaussian distribution with only diagonal entries in the covariance matrix and modeling the prior distribution as the standard normal distribution. This is the case of variational autoencoders in image reconstruction problems. But the difference of our work from previous works is that the correlations in Z are essential to solve the problem. This is because the given graph itself represents the correlations between target and observed nodes in the graph, so we cannot solve the problem if we ignore the correlations in the latent variables. So the main questions that we want to solve in this work are given as two. First, how can we consider the correlations of Z in variational inference? And the second is how can we run efficient and stable inference as a result of our modeling? Now I'll explain our main ideas to address the main research challenges of the problem. We can summarize our main ideas as follows for structured inference. So the first idea is to model the prior distribution of Z as Gaussian Markov random field to utilize the graph in probabilistic modeling. And the second idea is to introduce low-rank approximation to the covariance matrix of the distribution of Z to make tractable computation of the KL divergence term. The third idea is to propose unified deterministic inference to improve the stability and efficiency of inference. I'll explain each idea in detail in the following slides. The first idea is to model the prior distribution of Gaussian Markov random field to utilize the graph structure in the probabilistic modeling. This Gaussian Markov random field is a probabilistic graphical model which computes the joint probability of variables in a graph as in this equation. Here, the psi I and psi ij are called node and edge potentials respectively, and these two terms are the most important components of the Gaussian Markov random field. And the C in the equation is just a constant that we can ignore for now. In other words, this decomposes the joint probability into the multiplication of local potential terms, and the overall random variables have a high joint probability if the local potentials have high values. So this changes the problem of modeling the whole joint probabilities into modeling only the potential functions of the graph. And specifically, the potential functions are defined as follows with two parameters k and h. So this modeling is done with h and k, which have different roles in the modeling of Gaussian Markov random field. Here, k determines the correlations between nodes because it appears in both node and edge potential functions, and h determines only the self-information of nodes because it appears only at the node potential function. The question is how to choose those two parameters from only the given graph without requiring parameter estimation. First, since h determines only the self-information of nodes, we can set h to 0 to model the zero mean distribution of latent variables. This does not decrease our modeling capacity because the latent variables can have any mean or any bias based on our choices. And more important is how to model k. And we set k to the normalized graph Laplacian, which is defined as follows. This modeling of k satisfies the constraints of Gaussian Markov random field, which are first, k is a positive semi-definite matrix, and second, the non-zero entries of k correspond to the edges in the actual graph. As a result, this Gaussian Markov random field-based prior allows us to rewrite the KL divergence term as follows, which includes k as a structural regularizer. This is the result of parameterizing the distribution of Z as a Gaussian distribution whose mean and covariance are represented as U and sigma. So based on this rewritten KL divergence, we can regularize the distribution of Z, but there are still challenges that need to be solved. The second question is, how can we efficiently compute the log determinant term in the KL divergence because the naive computation is n cubed, where n is the number of nodes. Our idea is to apply low-rank approximation to the covariance matrix by assuming the low-rank structure of sigma matrix as follows. Here, beta is a hyperparameter for the diagonal terms, and V is our new node embedding matrix to model the covariance matrix. As a result, we can rewrite the log determinant term as follows, where I sub r is the r times r identity matrix. The complexity of computing this term is linear to the number of nodes, and r is much smaller than n. So this makes the whole computation much tractable. Our last idea is to improve the stability of inference by unified and deterministic modeling. We observed that the node embedding matrices U and V play very similar roles in the KL divergence term. You can remember that U and V are designed to model the distribution of Z in the Gaussian distribution, and U is for the mean of the Gaussian, and V is to model the covariance in a low-rank approximated form. But we can see that I skipped in these slides because of the limited time, but we can see from the KL divergence term that these U and V matrices have very similar roles. So our first idea is to unify those two matrices as a single embedding matrix E and generate this matrix from our encoder function instead of generating both U and V at the same time. And another observation is that stochastic sampling of latent variables is very unstable in our case. Previous works on variational inference sampled latent variables Z in a stochastic way from a Gaussian distribution or any parametric distribution of Z. This is possible because they sampled Z independently for each sample, modeling the independence between those variables. But this is not effective if we consider the correlations of Z as in our case, because we need to sample those variables simultaneously for all nodes at the same time. This increases the space of sampling to exponential with the number of nodes, and this decreases the stability of the whole inference process. So we generate the latent variable Z deterministically from the embedding matrix E instead of doing sampling. This is equivalent to using the argmax function for generating Z from its parameterized distribution. There are two main advantages. So first, we can greatly improve the stability of inference, as I just said. And the second is we can still utilize the KL divergence regularizer on the distribution of Z even with this deterministic modeling. These two figures compare the naive computation or the naive stochastic sampling way of Z and our deterministic generation of Z. We use a unified encoder to generate a single matrix, which is then used to deterministically generate Z for the remaining process of predictions. If we summarize our three ideas, we propose idea 1 to model the correlations of latent variables by introducing the Gaussian Markov random field prior. And we propose ideas 2 and 3 to improve the efficiency of inference by a low-rank approximation and the deterministic inference. Our three ideas result in our final objective function L consisting of three different terms. The first two terms are for our reconstruction errors for the features and labels respectively, and the last term is our proposed regularizer on the distribution of Z. So the training of our model is done by minimizing these three terms at the same time as a single objective function. Now I'll introduce our model structure. We propose SVGA for feature estimation, which stands for Structured Variational Graph Autoencoder. Our SVGA is a GNN-based autoencoder for dual estimation of features and labels, where the first encoder app generates latent variables from the graph structure, and the decoder networks make estimations of features and labels from the latent variables. And as I said in the first part of this presentation, the labels are optional, so our model can work even when the labels are not given. If we specifically look at the models of this structure, we first use a simple graph convolutional network as the GNN encoder app. And we make an identity matrix I as an input of this encoder network to allow app to learn independent embeddings of the given nodes. And we use multi-layer perceptrons as the encoder networks G sub X and G sub Y to estimate the features and labels respectively, ignoring the graph structure, which is already considered in the GNN encoder function. Then we minimize our objective function L, which consists of two reconstruction errors for the features and labels respectively, and our proposed regularizer on the distribution of Z. The training is done in an end-to-end way by updating the parameters of the GNN encoder and MLP decoders at the same time. Now I'll explain our experimental results. We compare our SVGA with various models proposed for feature estimation, including VAE, GCM, GAT, and so on. We use 8 data sets of undirected graphs containing either binary or continuous node features. This is a summary of our data sets, and 5 data sets contain binary features and 3 of them contain continuous features. The number of features that we aim to estimate as our problem varies from 300 to 6,000. The first question is how accurate is SVGA in feature estimation? Our SVGA works best in both binary and continuous features as shown in these 2 tables. We use 2 evaluation metrics for each setting, and our SVGA works best in most cases of experiments. We show only a subset of experiments due to the limited space, but you can see the full results in the paper. And the second question is, does SVGA help node classification? Our SVGA works best with 2 different classifiers. So this experiment is based on the idea that the good node features will help increasing the accuracy of node classification if we train a classifier based on the generated node features. If we train 2 kinds of classifiers, MLP and GCN, based on the generated features, our SVGA outperforms all baselines with those classifiers, achieving the highest accuracy of node classification. The third experiment is to answer the question, do observed labels help node feature estimation? So in the previous experiments, for a fair comparison with previous works, we assume that no node labels are given for experiments because previous works cannot use the observation of node labels in feature estimation. But in this experiment, we changed the ratio of observed labels and see how the performance changes based on the ratio of labels. And as shown in these 2 figures, the additional observation of labels improves the accuracy of estimation. And this means that the dual estimation of features and labels is effective for learning better representations of nodes or latent variable C. Our last question is, how does running time scale with the graph size? From this figure, we can easily see that the running time increases linearly with the number of edges, which is essential for the scalability to large Euro graphs. And the running time is instant even for large graphs, which is less than 100 milliseconds. So let me conclude this talk. In this work, we propose SVGA for solving the problem of feature estimation. The main ideas of SVGA are summarized as follows. So the first, Gaussian Markov random field prior of latent variables. Second, low rank approximation of the covariance matrix. And the third, unified and deterministic inference. As a result of these 3 main ideas, we can propose a new objective function for the training of the whole model. And we could achieve state-of-the-art accuracy in 8 real-world graphs containing both binary and continuous node features. Thank you for listening to the talk. And this is the homepage of, this is my homepage and the GitHub repository of this paper. You can get the data set, paper, and the implementation of our work in these links. Thank you very much.